Hello, this is Joo-Seung Kim, period 3, Farrar, and I am going to talk about absolute convergence. So what is absolute convergence? Well, the basic definition is that when the summation of the absolute value of a of n converges, then this is what we call absolutely convergent. So what this implies is that a of n, the summation of a of n, converges, and the summation of a of n times negative 1 to the n also converges. This is especially useful when you're trying to classify the series. However, there is another concept within absolute convergence, which is called conditionally convergent. What this is saying is that there is going to be an a of n that diverges. However, its counterpart of negative 1 to the n of a of n converges. When one of them converges and the other one diverges, this is called conditionally convergent. But because this function is always going to be less than this function, this series is going to be less than this series because we see any given series, it's like a of 1 minus a of 2 plus a of 3. This is always going to be less than a of 1 plus a of 2 plus a of 3. So therefore, when we do conditionally convergent, the only thing we're looking out for is this divergent. And going back to absolute convergence, there are two tests that will help us in finding absolute convergence. It is the ratio test, and it is also the roots test. So these two tests are really convenient because they either tell absolute convergence, divergence, or it's not going to work. Because there are going to be other videos put up about the ratio and the roots test, I will not get into deep meaning about this. However, basically it states that a of n plus 1 over a of n, when it is less than 1, when the limit as n goes to infinity, when that is less than 1, it absolutely converges. And this is also true with when the limit of n goes to infinity of the nth root of a of n. However, when they are both equal to 1, it fails. The test does not work, and there must be a different way in order to find convergence or divergence. The last one is when it's greater than 1, and this one is just divergence for both of the cases. So this is really convenient because if you have a function that you're not really sure about what to do with, if you use the ratio and the roots test, you can easily find whether it is absolutely converging or diverging. And because it's such a simple test to use, even if it fails, not a lot of time is wasted. Now, going back to conditionally convergence, we will look at an example of a very basic, very elementary harmonic series. 1 over n. Now, we all know 1 over n diverges. However, negative 1 times 1 over n when negative 1 is put to the nth power, and you find the sum of the series, we see that by the alternating series test, this one converges. The limit as it goes to infinity is going to go to 0. And 1 over n plus 1 is going to be less than 1 over n. So therefore, this one converges. So we see that one of them diverges and one of them converges. This adds another layer of description to our test. Now, absolute convergence in itself is not difficult. It is very easy to think about. It's very easy to understand. However, the hard part is using the tests in order to figure out whether it converges or diverges. And the hard part about this section is that there are so many test cases that can be solved, and there are so many ways to solve it. We learned about P-series, we learned about harmonic series, we learned about integrating the function, integrating the series. We learned about comparing, we learned about direct comparison and indirect comparison. And just from the sheer amount of tests that we learned, this easy concept becomes difficult. However, some ways to circumvent this in order to lessen mistakes. We use the principle of direct comparison. And we know that a of n is always going to be greater than negative 1 to the n of a of n. So with this idea, we can implement many tricks in order to figure out whether it converges or diverges. If this one converges, then this one's forced to be convergent. If this one diverges, this one's forced to be divergent. So if a function looks as if it's going to diverge, then try to figure, and you can't use the ratio and the roots test. If they both fail when it equals to 1, then try to find this. And if this turns out to be convergent, then sorry, you have to figure out what that is. But if this is divergent, then this also is divergent, so it's just divergent. However, if this is convergent, then this is also convergent, so it absolutely converges. However, only when this one diverges and this one converges does it become conditionally convergent. Therefore, this one is the superior function to solve for when you are trying to find out whether it absolutely converges or it conditionally converges. Just as a quick review, we see the two tests that we learned about, ratio and root. We know that if a of n plus 1 over a of n is, as n goes to infinity, if it goes to less than 1, then it absolute convergence. If it's equal to 1, then we don't know. And if it's greater than 1, it is divergent. Same with the roots test. Except for now it's the nth root. Finally, we have the definition of absolute convergence, where the absolute value of a of n, the summation, if that converges, then it's absolutely convergent. And we know that it's conditionally convergent when this one is divergent, but this one is convergent. And lastly, what we learned was that there is a significantly easier way to do this, easier way to figure it out if ratio and roots tests don't work, and that's figuring this out. So that if this is convergent, then the whole thing is convergent. And if we figure this is divergent, then the whole thing is divergent. Thank you for listening.